am thrilled to welcome Carl W. Hanlin Wallace, former head of data science and artificial intelligence at Rappi, a unicorn in Colombia. Carl is an actual head of data science and artificial intelligence for Rappi. He has over 8 years of experience in the areas of applied data science, machine learning, and artificial intelligence. Extensive experience in fintech, insurtech, and proptech, an open source and an open data enthusiast, Python programmer, part of the organizing committee of the meetup, the Data Pub, for Mexico City. Carl will join us from Mexico. Today, Carl will share his experience with machine learning and model monitoring in production. Carl, take it over.
Hi everyone. Thank you for joining me. So today we're going to talk about a little bit of machine learning model monitoring in production. This is something really hard to understand for me as well, coming from a traditional background. Still, it wasn't called machine learning yet. It was data mining. So it's going to be interesting, and welcome everybody. So just a little bit about me. I was the former head of Rappi Artificial Intelligence. Right now, I'm founding my own startup named Truly, and we believe in gathering data and doing analysis from the data help us understand the big problems from now. Truly now experiences in dealing with fraud, actually detecting and preventing fraud. And what I'm going to talk about here, it's about how do we use this data. We use them to build models, and then these models go into live production. And there's a missing link between those steps that we are going to talk today, which is monitoring. So thank you for joining me. So let's talk a little bit about the machine learning cycle. So when talking about the machine learning cycle, we usually, as I said before, I come from a traditional background. I was studying this topic around 9 years ago, and we will still call it data mining. So we will usually, and I know most of you are familiar with this type of processes, which is CRISP-VM, the cross standard processing for data mining. The process usually stops at deployment. We know it's a hard process that usually starts from the data, from the business question, the business understanding. Then we go from data understanding to the preparation of the data. We finally get to modeling. We do our models, machine learning model, supervised, unsupervised. We evaluate the model, get some information about how we think it's going to behave in production. And usually the last step, which was at least the hardest step back a couple of years back, was deployment. How to deploy it in a highly scalable, highly concurrent environment that can process a lot of queries. And this is something really hard. I mean, at least in the last reports, only 87% of the projects, at least for data science, go into production or deployment. So this is something big. Achieving this whole cycle is something big. So it's hard to get there, but then we forget about maintains, about how the model is actually behaving in a production environment, and then when does it need to be giving some updates. And this is something we always forget. I think the question that usually get asked more is how do we make sure that the model continues to generate the desired productions as we think in the evaluation phase. Right? So there's clearly something wrong with the CRISP-VM cycle, and then we usually use updated version of the machine learning cycle that actually include a very crucial step, which is monitoring. So there appears to be a missing link, what I was telling before, which is monitoring. Something that will help us understand how the model is behaving in a real production environment, and how it's still making those predictions in that environment. So this missing link, of course, is monitoring. Yeah. And if we look about the most recent trends, especially the most hot topics right now, which is machine learning operations or MLOps, if we take a look into this mix of machine learning, data science with DevOps and software engineering, we actually looked at the only way to close the loop. The only way to close the loop from these processes, these operations, is to actually get a monitoring services that can bring us data of how the model is behaving, not just the software, but how the model is behaving, so that we can set up some triggers, alerts, gather the data, so that we can actually close the loop and start the cycle again of data extraction analysis, going with the data scientists, building better models with better feedback, and then using these automated pipelines to create new versions of the model that we can serve as prediction services, and will update of monitoring services, so that we can see if the model is behaving better or worse, if the model is making better predictions or worse. So this is something that we might actually see in the most mature ML infrastructures, that they have a solid monitoring service that is actually connected with some actionables. If they had triggers, alerts, and the data goes back into the warehouse, goes back into the into a repository, whatever, so that we can actually have a 360 view of how the model is behaving. So what I'm here to actually talk about is a little bit of why and how. So make a little bit clearer what monitoring means, what this especially this phase of monitoring means, and why it was so hard for us, at least coming from a more traditional background, to get this mindset into monitoring and actually get the better concepts of software engineering, so that we can actually take the better of both worlds. So the thing I want to start with is why monitoring. So it's hard to think about a real world data that is not stationary, right? That is stationary, sorry, that doesn't change. So real world is rarely stationary, it always changes. I mean, I think the reality check that we had in 2020, which was the beginning of the pandemic of COVID-19, was the better example of how it broke mostly every system and every prediction system, right? From the face recognition software not being able to deal with the face mask, with the different trends that change from night to morning about the different consumer behavior, prediction on sales and inventory, everything just crashed. And I mean, this was not due to a lack of proper monitoring, of course, but the adaptability of dealing with this type of concerns and this type of unforeseen events. It's why monitoring is important. It's not that we can be always 100% prepared, but it's that we are prepared to be able to deal with this type of events. So when talking about machine learning, we usually have a new layer of complexity, which is data. With not is not code anymore. Like the traditional software system or software engineering, we are dealing with codes, inputs and outputs as well. But here we have an extra layer of complexity. Even if the data input is okay, the predictions might be wrong or the outputs might be wrong. So we have this new layer of complexity we need to think about in terms of monitoring. So a lot of things can go wrong in production environments. Software engineers and developer operations people know this well, but we can classify them in at least in the machine learning environment into two groups. We have the system or the traditional software problems where we know how to check, we know about service health, response time, latency, critical errors, uptime, everything that usually the persons in charge of monitoring traditional software base their alerts of that they can see if a system is behaving correctly, is working correctly, what to do in case of an emergency, and so on. But with the machine learning, is not just system anymore. We have data inputs and model outputs, as I was talking before. So data inputs is the data that go into the model. It can be images, tabular data, whatever, but it's the data that actually fits the model, the information. So in here, the problems that we can have is input drift, broken pipelines, missing values, data outage. So whatever affects the inputs of the data that goes to the model, which is critical for producing an answer. And then we have the model outputs. Right? So where we have a concept drift, what we are going to talk about in a little bit more minutes, but we can have a change in prediction distribution, model performance. We actually have can have biases or making predictions that undermine different classes. So this is the problems that we are going to talk about now, and why monitoring these problems is important. So we know how to deal with system monitoring. We have been doing it a lot, and now with all the cloud infrastructure, is easier than ever to actually build this type of dashboards reporting, and to be on top of the behavior of the system. So we have metrics like latency, memory usage, health pings, CPU rate, errors 500, error rates, and so on, to try to give us a clear understanding of how the system is behaving. Yeah, a lot of software we can use Grafana, Dynatrace, Datadog, New Relic, you name it. There's a lot of competitors in this realm, but it's hard to find something similar, at least in the last years, something similar for model monitoring. There's a lot of new trends, and there's a lot of new companies actually dealing and tackling these type of problems. But this is something that before going to the software, we need to understand ourselves so that we can either build it in-house, understand the problem, and then we can, if something suits, we can go out and look for a provider. But we talk about, okay, what are the metrics of the data? What are the metrics of the model that we can actually start monitoring to be on top of the behavior of the model? So in that case, I think something that summarizes it is model decay. This is what we are going to be looking at, or why are we monitoring, or processes that we are looking for model decay. The fact is that no model is forever, but the speed of decay varies. And just to summarize, what is model decay? It's the degradation of the model accuracy over time. We were telling before that no real world data is stationary, so we need to keep updating our data. We need to keep updating our concept of the thing we are going to predict, and that actually translates into model decay. So every model in production is going to start to see degradation over time, in either in accuracy, if whatever score we are looking, even the business KPI we are measuring, it's going to be to start decaying. Not all models decay at the same speed. Something do more or less in different times. But consider this: if we have the different components, we're talking about data inputs and model outputs. If we have model input data such as features, which is the main source for our model, and then a model prediction, what we're going to call y hat, and the true label population y, then we can start defining what causes model decay in terms of these terms. So what causes model decay? In this case, we can have different mixtures of these model components that might cause model decay. So we were talking about the concept before, the concept drift. Is a change in the true label given the features. So a change in the relationship between the input and the model true label. This is the most crucial drift, because is the one that is going to change the reality of the model. If we, for example, have a model that predicts or help us predict customer behavior for a given credit, this is going to change over time due to macroeconomic features, due to the people that are coming into our application or into our business. Actually, a lot of things can start going to change the concept drift, but it's actually this thing. This is something that we might be more on the lookout about, this type of accuracy that might suggest that the concept is different, and that we might need to retrain our model based on new data, new information, and new labels. And we are going to find it in two flavors: either virtual or real concept drift. The main difference is that with virtual drift, we might see a change in the distribution of the variables, especially in the input variables, but no change in the output label. So the concept is the same, but we see a shift in the population going, but the concept holds. But in the real concept drift, which is the one we're looking for, trying to be on top one step before, uh, is about that relationship, that the people coming, maybe because of macroeconomic, something like the pandemic, it's going to change the way people behave, at least if we see it in the example of the credit. Then we can have a prediction drift. As I said before, for example, in something credit, it's going to take a lot of time to actually detect concept drift if we start to look into the with the true labels, because to detect it we need the true labels. But we can actually do some proxies, and especially with prediction drift, when we can see a change in the prediction label with the information that goes into the model, so that relationship, especially distributions and so on, then we can be one step forward that something might be not so good, that might translates into concept drift. Then we can have also label drift, a change in the label or a change in the distribution of the label, the true label, of course, and the feature drift, which is going to be something as the first line of defense. So we expect certain distribution of the different features that go into the model. For example, in the type of credit, we can have age, gender group, and so on. So this type of distribution is going to talk about the distribution that goes into the model, this feature. So this is a change into the features that go and actually fit the model. As I was telling before, this model decay rate isn't the same. It can happen in different times, and it's being classified in four different groups: either sudden drift, or that the new concept changes really fast in a short period of time. This is, if you can imagine, something that happened for like with the COVID pandemic, uh, that all of the sudden there was a drift into the concept. All the model is not able to perform anymore, and we need to do something drastically. And this is something of an outlier. The reality is we're going to deal with either gradual or incremental shift, where over time the model is going to lose accuracy and it's going to behave badly. And this type of gradual shift, for example, as I was talking, the credit is a very good example for actually looking into this type of drifts. Changes gradually. For example, population changes, consumer behavior changes, macroeconomic variables changes, and this is going to actually translate into a concept drift either gradually or incrementally. And then recurring concepts, which is the shifting or the constant shifting of this concept that actually goes back and forth, and then we might need to capture, if we detect the drift, we might need to capture into a more general model. Now, when dealing with drift, uh, as I said before, the consequence of this drift might have many culprits, but data quality, data issues, model inputs, and model outputs might be the something to start. But with the dealing with drift, I think the first thing we need to do is to ask ourselves: is the data quality it's okay? Because the first thing that happens, especially in a production environment, is problems with the inputs of the data that might cause us problems, of course, of the model output. And I'm thinking about model broken pipelines. I don't know if if you have dealt with this before. Schema changes from the database, infrastructure updates, broken features, missing values, third-party data provider changes in the APIs or whatever actually brings the data into the model. And this might be the first culprit we might need to start checking. Okay, there's something wrong with the data, and we can use the traditional system verifications of data engineering to actually check everything is okay with the data. If everything is okay with the data, but we have concept drift, then something is a little bit harder to understand. So in this case, we have the tool of drift analysis. If that is okay, if we have verified that the data is correctly pulled from the database, is correctly pulled down from the different API providers and so on, then there might be real change. So we need a way to deal and detect this type of drifts. And we usually use drift analysis for this case, which is nothing more than comparing current data for some reference data. So it's actually comparing how the model is behaving right now with the way we intend to be behaved. How the distribution of the features is right now with the distribution of the features of the data the model was trained for. So the most common reference is for use the training data set, no? Or have something of a window of a data set that we can use for comparison. Mhm. In this case, we can see, for example, if we have a model that uses information about humidity, we can actually see how the distribution changes and how big is the distribution, and we're going to see some statistical tools for actually measuring that different the difference of distribution. So the different types of drift that we can have now, when we know it's not caused by the data, but we can have a real change. The first thing is to go into checking if we have performance drift. I think this is the most straightforward to understand, but it's the hardest to have, and I'm going to say to you why. But it's the most straightforward in the sense that is the way that we measure how the model is performing. Take, for example, in this case, we deploy the model into production. We use the F1 score to actually measure the how the model is behaving, and we are going to start to detect some decay. After, we need some threshold that actually impacts the business. Okay, we know below this threshold, it is going to cause any more good for the business, then we might need to retrain it, get a little bit more data, the data that was produced actually in this period of the model going into production, make a new version of the model that is going to again uplift all the measures going into production, and so on and so on. However, and now I know you already detected why it's so hard to actually perform good performance drift is that we need the ground truth and the labels. So it's not always possible, especially in models that go, for example, with credit or fraud detection. We might need to take a lot of time to actually get the right information. So we need something similar like a proxy. In that case, we can use prediction drift. I was telling before, checking the output of the model. If we perform, uh, for example, a distribution comparison of the different labels produced by the model, we might need to expect that the model is behaving at least in the same way that it was trained. So in that sense, it might have the same, or at least in some terms, the same distribution of the population that we were expecting. Right? So in that case, if we have some change in the prediction labels, that this might underline that there is something behind, or that we could have some concept drift. However, we don't need the ground truth or labels for detecting prediction drift, so we can use just the outputs of the model to actually do it. Input data drift, which is I think the most useful one, at least when you are starting to work with monitor. I will suggest, when checking the data is right, then going straightly into the data drift, because if there's a change in the population, this is going to be a change into the model behavior, right? At least in the distribution of the predictions, but that might have an impact, or that might have an impact, or at least some hints that the concept might be drifting. Right? In this case, we're going to take the distribution of the input feature that we are going to look out. For example, we can say age or whatever input of the model is going to be, and then compare it with the reference or the training model. In that case, so uh, just how do we detect drift? At least I was talking about the prediction drift, the concept drift, and the feature drift. If we have the labels quickly, what I was telling you before, that we can do uh, a, a prediction drift, sorry, a performance drift, sorry. We can use then statistical measures of how the model is behaving. We can do a population comparison. We can use statistical metrics such as mean, standard deviation, the distribution, and so on. But we have other types of tools of the drift detection method, early drift detection method, consume page Hinckley, and Atwin or adaptive window that we can use to actually detect this type of drifts. Mhm. And if we don't have the labels quickly, then statistical methods such as comparisons of distribution, like the Kullback library divergence, population stability index, which is really popular, at least when dealing in credit and banking, and a little bit more traditional models. Uh, Also, Jensen-Shannon divergence, which is symmetrical Kullback library divergence, all the Kolmogorov Smirnov test that might give us a comparison of the different distributions. And then how I mean, there's no such thing as a objective or perfect test that will actually help us, but we need to have a sense, understand the model of how it's behaved, so that we can see how this drift is going to affect us. So finally, the thing for us, I think, to be closing the talk, is always alert, keep calm. I mean, this is always going to happen. It's easy to be one step ahead if you know all these tools and all the problems that you can have with your models in production. At least that's something of a hard lesson that we needed to understand, at least in our ecosystem here in Latin America, and especially in Rappi. But is prepare your alerts, keep calm. It's always going to have, there's always going to be problems with the input data. There's always going to be problem with the concept drift. So defining some, at least rule of hand, uh, a street lights of how big is the problem. We can define, for example, if we see a change in the PSI, population stability index, we can do keep monitoring. If we see a significant change, then start thinking about doing something. So if drift is detected with this alert, first check the data quality, investigate, retrain if you can, if you had more data, rebuild if you need, if something is broken from the inside. Then if not neither of those work, we can always think about a fallback strategy, something that we have done before. If thinking about a shortage of the model, then what will be the fallback strategy? This is going to be manually reviewed by a team, so on. Then if something's really wrong, we can limit the model use, start thinking about the fallback strategy, and finally add custom processing logic if something goes really wrong. So I think we still have 3 minutes for questions. I think this was all. I'm happy to answer. We can go here.
Okay, let's see. Faye Marie Sina Cruz asks, data the model sees in production is constantly changing. How can we leverage machine learning in business KPIs? What are the best practices to monitor ML production?
Question. I think, at least in a business environment, business KPIs are the most important. So when you are designing your monitoring, I was talking about input data and so on, but actually the best thing for the data scientists and model developers is to be on top of the KPIs of the business. How is it behaving, and what percentage of the, for example, failure of the model is going to affect my KPI? Because this should be the main flag about how the model is performing. As I said before, it's not so easy to actually be on top of the business KPIs, because they might take a lot of time to actually come back. Especially in credit, we might need to wait 6 to 10 months or 12 months, whatever. We need to see if we have some early metrics, okay, but it's going to take a lot of time. So we can, even though we need to be on top of the business KPIs, we can define our own early alerts, early signs that something is going wrong, so that we don't need to wait when the KPI starts underperforming to be start looking for culprits that something is wrong with our models in production.
Okay, we have about 90 seconds left. Why don't you take a look at that list of participant questions to the right and pick a winner for our most thoughtful question contest, so we can award a prize.
There's a lot of questions, really good. So there's a machine and learning AIs that help banking in production. How do you identify the machine learning model is seamless and addressing the requirements in terms of monitoring production? I think that was a really good question. And actually, I mean, addressing the requirements, at least I think it goes back with the business KPI of actually understanding the business. I mean, we do models to actually improve our processes, improve our KPIs. So this might need be the first requirement. If we have something that can be improved, and that we have the capabilities of doing a model or doing, and of course the data, then we can do those as the requirements. But the main driver of these type of systems should be and need to be the business as well.
All right. Thank you, Carl. That was a great talk. Thank you for sharing your insights on ML ops and monitoring. For the audience, stay tuned. We've got more talks ahead. Thank you, everybody.
Much.